everybody. Is anyone in the audience familiar with the Philadelphia experiment? Well, so in this experiment, there was a US warship, Eldridge, at Philadelphia, which was made to disappear in a flash blue light, and then at the same time reappear at Norfolk, Virginia, which is about 200 miles away. Now this story, which later turned out to be a hoax, was nevertheless based on some really solid fundamental principles of quantum mechanics, which we call teleportation. And I hope most of you will be familiar with that. So today, I will not talk about the teleportation, but I will talk about quantum computation, and teleportation is one of those concepts. I'll actually describe in my agenda the basics of quantum computation, quantum computers, and how do we get a speed up in quantum computers, and that will be followed by a question and answer session. So remember, quantum mechanics is really weird and bizarre, but quantum computation is really interesting. So what is this quantum computation about? Well, quantum computation is actually an overlap of computer science and physics. And quantum computers, well, they use some weird principles of quantum mechanics to do useful computation. So just to give you an idea of a difference between quantum computer and our modern computers. So in our modern computers, we have a fundamental component of processing and storing of information, which is transistors. And the fundamental unit of information is bit. Whereas in quantum computers, we have atoms, and the fundamental unit of information is a qubit. It turns out that in terms of power and performance, quantum computers will be much faster, and they will consume very, very small amount of power. It also turns out that quantum computers can even do those calculations which even your modern day supercomputers cannot do. And whosoever will give us the right answer in the Q&A session will win some reward. Now that we have looked at a high-level overview of a difference between quantum and modern computers, let's figure out some of these details. So we have a bit and a qubit. There's not much of a difference between these two, right? So if you have a bit or a qubit, you can represent two numbers, 0 and 1. Similarly, if you have 2 bits, you can represent 4 numbers. 3 bits, 8 numbers, 0 through 7. But a bit or bits can only store one possible value or number at one time, whereas qubits can hold all possible numbers simultaneously. So imagine if you have a 32-bit system, and that 32-bit system, those 32 bits can only store 1 out of 4 billion possible numbers. But a 32-qubit quantum system can store and actually play with 4 billion numbers simultaneously. And it is because of this ability, quantum computers can look at several possibilities at one time. It can play with multiple things at one time, whereas a normal computer, it can only do one thing at a time. So this ability of holding multiple values simultaneously, which gives quantum computer an edge over modern computers, is known as principle of superposition. And it is the principle of superposition which gives us an essential speed up in quantum computers. And suppose if you have a modern computer which is searching for some particular entry in the database, and suppose it takes 1 hour to complete this task. The same task your quantum computer can complete in principle, in theory, in 1 minute. So you people must be wondering that where did the superposition actually come from? So remember that quantum computers use atoms, and atoms are quantum mechanical, they exhibit quantum mechanical properties, and one of those quantum mechanical properties happen to be that atom can be in 2 different energy states simultaneously. and which is analogous to saying that a qubit, which is the unit of information which we store in the energy states of the atoms, can be in two different states or can occupy two different values simultaneously. And so in conclusion, today we talked about quantum computation, we talked about the qubit, which is the unit of information, and the principle of superposition, which gave us the essential speed up in quantum computers. Thanks very much for the listening, and I'll be happy to take your questions.
Yes, the first question.